Okay, looks like I'm going to be heading out. So I just want to make this video quick about power for you. So power is change in energy over time. All right? And this could be any type of energy. This could be change in PEG over time. It could be change in PES over time. It could be change in kinetic energy over time, or just simply work over time, work done over time. And work is, basically all three of these, right? So, quick example, which is similar to the the worksheet I'm going to ask you to do. The last few problems on worksheet 3, is it? Worksheet 2, energy, worksheet 2. Problems 10, 11, and 12 is to figure out the power of something that's going up. So here's an example. Somebody starts on the ground floor, all right, of someplace, and they run to the top floor. All right, so it went off the board a little bit here. So changes some height h. All right. Let's make it 3.0 meters. All right. Let's say they run up the stairs. Now, let's say they start at rest and they end at rest, right? So V initial V1 equals 0, V2 equals 0. So in each spot, they start and end at rest. So they're going to do work to overcome gravity to get vertically changed. So the power they produce is going to be equal to their change in PEG over the time it takes. All right? So mg delta H over T. So the power output, and the power is a capital P that is equal to, let's give them a mass, I suppose. Okay, 40 kilograms, let's say. No, let's say 60, make it a little heavy. 60 kilograms times G, which is about 10 newtons per kilogram, times the height they've run up, 3.0 meters vertically. This is the vertical height, not the actual distance here. If we knew their velocity as they were going up the ramp, we could also figure their average power output that way. But, this basically gives you, this is basically their change in height over time. It's basically their average vertical velocity, right? Divided by the time of, I don't know, let's say it took them 0.30 seconds. 0.30 seconds. All right, so let's do the math here. Power, 60 times 10 is 600, times 3 is 1800. 1800 joules in 0.03 seconds, or sorry, 0.30 seconds divided by 0.3. So 1800 divided by 3, that would be 60. But it's 0.3, so it's going to be actually bigger, right? It's going to be 600 joules per second. That'd be the power, average power output, 600 joules per second. Now, things look a little bit blurry, don't they? Maybe I didn't focus it well. I'll try refocusing it here. Now, that's better. All right, so that was 600 joules per second. So the power, we usually say average, equaled 600 joules per second. Well, 1 joule per second is what we call 1 watt, named after James Watt. That's the unit of power. All right. He invented the concept of watt. Okay, Watt invented the concept of power, and he used it to market steam engines to sell. And he basically determined how quickly his steam engine could move something versus a horse, right? And he called it horsepower. All right, so horsepower, well, it really was compared to a horse when it was invented, but today we don't call it horsepower. We just call it power. And we don't use horsepower, which is HP. We use watt. Turns out 1 horsepower, though, has been standardized to equal 746 watts. So this person produced just under a horsepower of energy as they ran up those stairs. Or power, I'm sorry. We don't ever use horsepower really in physics. We always just use watts. All right. For instance, if you look at a light bulb in your house, right? You'll see it's maybe, the old ones used to be 60 watts. Or let's say you have a computer and it has a 450 watt power supply, right? So that means that thing's consuming 450 joules per second of energy. So for 10 seconds of running, it would consume 4,500 joules of energy. Hair dryers, right? Hair dryers are crazy. They use something like 1,800 watts or 1,800 joules per second. And you'll see in this worksheet a number, or actually, I think that's on the horsepower lab, okay, which we're going to do here in school. You'll see they compare they have you calculate the total amount of energy that you would use in a certain amount of time. So one thing I should go back to with this equation here, you could rearrange this as change in energy. The amount of energy used is power times time. Power times time. So sometimes you see electricity company, right? You buy kilowatts times hour. Kilowatts, that's kilowatts. 1,000 watts, and this is hour. Kilowatt times hours. So that is an amount of energy. It's the number of watts times time. So 10 kilowatt hours it's not technically power, it's energy that you're buying from the quote-unquote power company, right? So it's kind of interesting. So this is power times time. Energy is power times time. But anyhow, you could convert this to joules, right? That could be done. Could figure out. All right. So actually, we could do that now. That's kind of an interesting thing. 1 kilowatt hour equals 1,000 watts times 1 hour. All right. Then watt is a joule per second, so I'll write it as joules per second. We need to cancel out the hours. So times, let's see here, 3,600 seconds per 1 hour. So everything cancels here. So 1,000 times 3,600 would be 3 million joules of energy in 1 kilowatt hour. That's pretty cool. Anyhow, pretty easy concept. I'm going to post this, and so if you need to go back and take a look at it, you'll be all set.